Are there any homework questions? We finished 3.1, 3.2, 3.3, and 3.4. Remember, for the time being, we're skipping 3.6, and that will be at the end of chapter 3. 3.6 deals with applications, and so does 3.11. So we've saved those two sections for the end of chapter 3. So we can get all the derivative rules out first, and then look back at applications. Good on the homework then? For now? All right. Good enough.
Was your weekend, did your weekend feel like really long?
No, never does. Why?
No, like all of us are just like, was it just me? And I feel like my weekend went by like so slow. I'm like, yeah, it kind of did. And I'm like,
Yeah. It's nice when that happens, but it rarely happens. Especially as you get older, time contracts. So it seems like time goes by faster than when. I think it's because when you're young, everything's novel to you. Right? And when you get older, it's like, whatever. I'm in the car again.
I'm going to work again.
Yeah, right.
So do you want to go to this concert?
All right. So in 3.5, we're going to get the derivative of our trigonomic functions. But before we actually look at those, we address these two limits. And these limits are used to prove or to determine the derivatives for sine and cosine when we're using the definition of the derivative. I know one of them's done in your textbook. We'll walk through another one once we get there. But again, these derivatives, you're not responsible for computing a derivative by the limit as h goes to 0 on the difference quotient. That's only if the question says use the definition, right? So all of the derivatives that we see are shortcut methods, and it's perfectly acceptable to always use those shortcut methods, except for on the exam where there's one question that will say use the definition. So just remember that, and I see people on the exam trying to do every derivative using the limit instead of the shortcut, and that's going to be super difficult. So it's just, for the time being, we will present at least one trig derivative using the definition so we can kind of see how it works. But then we'll look at the actual formulas for them, and that's all you need to remember. All right. So both of those limits come up in deriving or proving the limit for sine and cosine. And there are a few examples in your homework that you have to work through, so we're going to look at a few examples. These two limits here are not necessary to remember on the exam. So you don't have to remember these for the exam. So if you need it for 3.5's homework, you're not responsible for those two limits on the exam. Okay, so we'll look at a few examples, and then we'll get into the derivatives of our trig functions. I think it's important to note here, though, that when we look at the limit as x approaches 0, sine x over x is equal to 1, that these arguments are matching each other. So for instance, if we were asked to compute the limit as x approaches 0, we'll go to example 1, on the sine of 32x, oops, whoa, I got rid of the 1, the sine of 32x over 32x. The theorem 310 directly applies to that. Even though we don't see it as x, just think x is a placeholder, and those placeholders are identical. So since we have identical things, we can immediately apply that theorem and say that that limit is 1. Remember, limits where the numerator is 0, we can define as 0. Limits where the denominator approaches 0, we can define those essentially as infinity or negative infinity. So it's really only the sense of if we plugged in directly, here we would get 0 over 0. So those are the instances when we had 0 over 0 or infinity over infinity, where we had to do extra work, like simplifying involving the conjugate, factoring, whatever. Okay. Later on in chapter 4, we'll see a different method to take or to compute limits when there's 0 over 0 or infinity over infinity. Okay, so hopefully that's pretty straightforward. It's direct application of that theorem. Example 2, look at the limit as x approaches 0 on sine of 3x over x. So note that this is in a different form than what the theorem states, right? It's the sine of the argument 3x, but 3x is not on the bottom. So if we applied that theorem directly to that, it would be off. You'd be off by a constant. So the trick here is to algebraically manipulate this so that it does look like what's presented in the theorem. So any suggestions? Squeeze theorem? We could try the squeeze theorem, but the thing is we're dividing through by the x. So like if we had, let's just say for simplicity, we had 1 over x and 1 over negative x on either side. As x approaches 0, the left and the right approach infinity and negative infinity. So we could try to squeeze it, but we would end up squeezing it between two functions that are infinite.
Can we just bring the 3 out of the equation?
So can we bring the 3 out that's in there with the sign? Can we do that?
Because it's a limit, I mean, we can't, right? Or
Well, is that a constant times a function of x? So there's is 3 sine x equal to sine 3x? Is that the same thing?
No.
No, they're completely different things, right? One of them just says 3 times sine, the other one is sine of 3 times your input. This is, you've got to multiply your input by 3 first before you take the sign. So they're not the same, you can't pull that out. In the same way you couldn't pull out, like if I had the square root of 3, you couldn't just pull that 3 out of the square root operation and say it's 3, right? So we can't pull the 3 out. And if you need to put parentheses around the argument here, then maybe do that, I don't know. But you cannot pull that 3 out. Yeah.
I was gonna say, since for the first one it's sine 32x over 32,
Uh-huh.
makes it a constant, so 1. Couldn't you multiply the 3 by that constant of 1 and make it 3?
In the bottom or the top?
Yeah, in the top, or in the for number 2.
Yeah. So multiply 3 here. Like that.
Well, no, what I'm saying is pull the 3 over and set it to the answer. As in, have it towards 3 times the 1 to make it 3. But does that not work?
I'm not quite sure I follow. Like, what would it look like? Like, what would be different? How are you seeing it in your
Well, could you say
head?
for the top one, since sine 32x over 32x is 1,
Uh-huh.
wouldn't that be, could you say that sine 32, or sine of 3x over x is equal to 1 times the 3?
Well, yeah, but again, I think that is the correct answer. But it's if you look at it as it's the sine of x over x times 3, then that involves pulling that 3 out of the sign, which we can't do.
Okay.
But 3 is the correct answer. How do we actually see that?
you multiply the fraction by 3 over 3.
Yeah, right. Remember the theorem says that the argument of sine and this thing we're dividing by have to match. So if we say, if that were a 3x, then it's just a direct application of that theorem, right? But if we multiply the denominator by 3, what else do we have to do? We have to multiply the numerator by 3, so we're not changing the value of the fraction. So we're just multiplying the thing by a form of 1. So I'm going to rewrite that just so we're not. So I'll rewrite this over here. So we want that to match the argument of sine, which means we need to multiply top by 3 as well. Okay. So remember, there's really only 2 algebraic tricks that you can do to an expression that doesn't change its value. You can multiply it by a form of 1, or you can add in 0. So that's really your only options when you're working with expressions. And we saw that time and time again with the conjugate. It was always the root, well, whatever. It was always multiplying by a form of 1. Same thing with the LCD. When we clear out fractions, we multiply by LCD over LCD, right? That's another form of 1. So that's all we've done here as well. So what would that limit be then? Yeah, because now we have a constant up top. We have a constant times a function of x. So we can pull that 3 out of the top and then apply the theorem to this limit here. So let me see this right here is equal to our 3 times 1, which is 3. So then you could take this and say, well, what if I had sine 5x over x, or sine of 36 over x, sine of 36x over x? We could make that a little bit more generic through that example, but that's the process that we want to look at here for this particular one. Any questions on that? Maybe not obvious how we should start out, but hopefully after we've done that, it's pretty obvious. Okay, another variation. How about the limit as x approaches 0 of sine 5x over 3x? Any ideas for that one? Yeah.
Maybe multiply the top by 3 and the bottom by 5.
Okay, multiply the top by 3
And the bottom,
and the bottom by 5.
get a common factor between them. And then
Top by 3 and the bottom by 5.
We do that, so you can find the function by 1.
Yeah. So if we did 3 by 5 here, we're not. It's not a form of 1. So we're actually changing the value of that expression or the expression itself.
And even if you did that, if you can't put the 3 into the sine 5, so like while you're multiplying 3 by 5, it'd make 15x on the bottom, or it would make 15x on the top.
Right. Right. So if we did 15 by 15, how would that help? If it does. Remember, the key aspect of that theorem is that the argument of sine and what you're dividing by have to match.
Could we multiply both top and bottom by 5 over 3?
That would not be a form of 1.
That's not
No,
1.
no. 5 over 3, 5 over 3.
Okay,
5
so
over
multiply
3
top
over
and bottom by
5
5/3 and multiply the bottom by 5/3.
Yes.
Would that work?
no.
It's definitely, we're multiplying the expression by 1.
But it turns the bottom into 5x.
Right, so it turns the
5x,
bottom into
and it turns the
5x.
top
To
into
5 over 3 times sine 5x.
Right.
Yeah, which is not.
So the 5/3 up top
Yeah.
would be, we'd say that's here, 5/3
It works.
sine
Because
of 5x. And 5/3 times 3x is just 5x. So would that work?
Yeah.
Yeah, it's just like the last problem now. You've got the 5/3 on top as a constant. Sign's argument matches what it's divided by. So we have that limit is equal to 5/3. The other way to see that is, you know, it's the same thing that we're doing, but might be for others it might be a little bit easier to see. So we're dividing by 3 times x. Isn't this just 1/3 times the expression? Like, isn't this the same thing as sine of 5x over x times 1/3? Okay, so if we looked at it that way, we would say, well, that's just a constant times sine of 5x over x, and to deal with the sine of 5x over x, it's identical to how we approach number 2. Right? We would say, well, it would be nice if this were a 5 down here. Well, I can multiply that by 5 if I multiply the top by 5. So again, the thing in red brackets is the limit as x goes to 0, that's 1, and then we have the 5/3 out front. So it's, either way you approach it, it's the same result. Anybody have any questions on that? Okay, let me look at one more. Should be a little bit more. Okay, last one, we'll look at the limit as x approaches 0 of sine 5x over tangent x. So it definitely looks like it has nothing to do with the theorem. And at least in part it doesn't, right? At least the tangent x doesn't show up in either of those two from theorem 310.
Would we say tan of x is sine x over cosine x?
Yeah, so we could try that. Let's take that over here. So if we had sine 5x over sine cosine, definitely can do that, but
Does it help if I help us?
it doesn't fully help us, right? So it's probably not obvious at all, but what if we divide the numerator by 5x and the denominator by 5x? Multiply the numerator and denominator by 1 over 5x. So that's still 1, right? We multiply the numerator and denominator by the same thing. We're still multiplying through by 1. But at least when we look at it that way, at least the numerator, rather, sine 5x over 5x is we can directly apply to the theorem itself. So we could take care of the entire numerator with doing that. But then the question is does that allow us to evaluate the limit as x approaches 0 on the bottom or on the denominator? So I'll put the limit here.
Would we be left with 1 over 5x cosine x?
Close. Not 1 over 5x cosine x.
5x over sin x, 5x over sin x over sin x.
Yeah. So we would look here that in the denominator, we've got sine x over x, right? So let's take this denominator and split that up a little bit. So we're going to take this and write it as sine x over x, from that x here, times,
5 cosine x.
yeah. So we're gonna split it up like that. Is that all right? So then, that's our denominator. We can compute the limit as x approaches 0 on sine x over x with the theorem, and multiply it by, can we compute the limit of 1 over 5 cosine x as x goes to 0? Yeah, because cosine of 0 is 1. So that's how we need to break this up. We need to say that this is the limit as x approaches 0. Divide top and bottom by 5x. Right here. So we'll just compute the limit on top using the theorem. That's 1. And how we broke this up below, we said that was the same thing as sine x over x times 1 over 5 cosine x. So then we're going to use the theorem again. Let me just write this out. Just so we're looking at it in pieces. No, it's not technically proper to just apply the limit to one piece at a time. But both of those were computed with a theorem. We can compute directly the limit of 1 over 5 cosine x as x goes to 0. So we have 1 over 1/5, which is 5, yeah. So that limit is equal to 5. Sort of our side. All right, does anyone have any questions on that process? Yeah.
How did, in the denominator, 1/5 cosine x, how did that turn into 1/5 again?
Because cosine evaluated at 0 is 1.
Oh, you did, okay.
Yeah. So that's what gave us this 1/5. I'm just writing it down. Any other questions on that?
When you divide through by 1/5, so it's sine x over 5x, like how does that, the x pop up?
How does the x do what now?
It just pops up. Like we have the sine x over 5x divided by sine x over 5x cosine x. And that was because we multiplied by 1/5, right?
1/5 x.
1/5.
Yeah, top and bottom. And since x is approaching 0, we're not actually multiplying through by 1 over 0 because x is just getting closer to 0. Yeah, so it's basically from this point, we divide here by 5x and divide here by 5x.
In that second part there, limit is x equals to 0 of sine x over 5x.
Mm-hmm.
Or it should be sine x, sine 5x.
Sine 5x, yeah, I missed that right here. Yeah, sorry, that should be 5x, thank you. Yeah, from the original. did I? Okay, we didn't talk about it down here. Okay. All right. So there's a few like that in your homework. I just chose ones that were, could help you through the homework, perhaps without getting assistance from the homework itself. But now we'll look at finding the derivative of cosine x using the definition. Remember the definition of a derivative f prime of x is the limit as h approaches 0 on the difference quotient. So we need to compute that for our function. We're trying to find the derivative of, which is cosine x. So we'll compute f of x plus h, and then put that into the definition. So we have f prime is the limit as h approaches 0. Cosine of the quantity x plus h minus the function cosine x all over h. So the trick to simplify this difference quotient here is to remember the identity. However it was presented, cosine of x plus h, cosine of x plus y, cosine of a plus b, however that's presented. So that's the cosine of x times the cosine of h minus the sine of x times the sine of h. So that's how we want to rewrite the cosine of the quantity x plus h. Okay, minus our cosine. Again, you don't have to remember this. Just trying to give some justification to where these derivatives come from. And from here, we'll collect like terms. Two terms in the numerator involve cosine, so we'll take those together. Take these two terms here, this term and this term, and we'll factor out the cosine. We'll have cosine x that we factored out. We're left with cosine h minus 1. And then we still have this minus sine x sine h here, all over h. Okay. So the trick here at this point is to split this up into two. So we're going to have our cosine pieces over h and our sine pieces over h. Just split those up. Is everybody all right with where we're at? Do you have any? Yeah.
I was just wanting to know where did the minus sine x and sine h?
It's part of the identity when we broke up cosine of x plus h. So that was the sum identity for cosine
Oh, okay.
and sine. Remember with sine it was like the sine of x cosine h plus sine x cosine h. Those sum identities, which is where the double angle identities come from. So that was just a byproduct of that identity. Now yeah.
Wouldn't the limit of zero sine x, sine h over h just become sine x times 1?
Yeah, right. So that's where those two limits that we referred to in the first page come in, because the limit as h approaches 0 on that cosine of h minus 1 over h, that was one in the theorem, that limit is equal to 0. And notice the limit as h goes to 0, it doesn't affect the cosine x, right? Because it's just h operating. The cosine of x rather, or anything involves x here as h goes to 0. Anything like x or y or w, anything that does not involve an h is a constant. And so this cosine is really out front. So it's still a cosine of x. That limit, according to the theorem, is 0. And we get the same kind of thing here. The limit as h approaches 0, sine h over h. That limit is also defined as 1. By the theorem. So we have cosine of x rather times 0 minus sine x times 1. So we just end up with minus sine x. So that tells us that the derivative of cosine is negative sine. So remember when we graphed derivatives? So when we graph, given a function cosine x, if we look at the function where it has peaks and troughs, we have horizontal tangents, right? So horizontal tangents on the function correspond to what on the graph of the derivative? X-intercepts, right? Because horizontal tangents are simply when the slope is 0. So if we put in here negative sine, notice everywhere the function cosine has a horizontal tangent, the slope of that tangent line there is 0, therefore the graph of its derivative is 0. Horizontal tangent here, the derivative has a 0 there.
Are the derivatives of each other? So the derivative of negative sine x would be cosine?
Not quite. Yeah, they're closely related, but they're opposites. Oh, sorry, that's the wrong one. This is the one we're after. Okay, so where cosine has horizontal tangents, that's where the derivative is 0. So we can see all of these horizontal tangents of cosine corresponding to zeros on the negative sine function, not positive sine. So here's where cosine has a horizontal tangent. Sorry, here's where cosine has a horizontal tangent. Sine happens to be 0 here, but not here, right? Horizontal tangent here, here. So I don't know if that's a visual verification, assuming that you remember, how to graph a derivative given a function, which you should. But again, we can verify that visually as well. And then we can go through that in a similar way to get the rest of these. So here's the derivative of all 6 of your trig functions. Again, this is just something you need to know, because even within this 3.5, they say here's the derivative of the 6 trig functions. Now, what happens if we look at how to take the derivative of sine times cosine, or 1 plus tangent over secant? So then you've got product rules and quotient rules applied in this section as well. So it's not like they just give you the derivative of something and then ease up on the other ones you've learned. It's a combination of both with every section. So it just keeps compounding. So something like this again is perfect for like a note card or a flash card or whatever. Just looking at those like a couple of minutes every day help a lot. The mnemonic here though is, if we can remember these 3 on the left hand side, if I can remember those 3 derivatives, then the mnemonic to remember the other 3 derivative is replace these functions here, replace with co-functions. We replace those with our co-functions, and then these results here, we negate those. Negate with co-function as well. So if I remember the derivative of tangent is secant squared, then if I put the co in front of that, the derivative of cotangent is not cosecant squared because I have to make it negative. Derivative of cosecant is, derivative of cotangent is negative cosecant. Replace secant with its cofunction, cosecant. The derivative is negative cosecant cotangent. So I don't know if that's helpful or not, but, and if we look at, the only one that's kind of weird is the top one. If we put co in front of sine, that's pretty straightforward, you get cosine. But cosine, you just kind of have to remember that that's like a double negative. 2 cos give you a double negative. So cosine, you're back to sine. So that's the only one that's a little bit weird.
Would you ever require us on the exam to solve the derivative by definition?
No, it would be, like, there is one question on the exam where you have to use the definition to prove the derivative of something is something,
Okay.
but they're algebraic functions.
Okay. Generally speaking, memorization
Yeah.
is going to be the most time efficient. Where you're not going to,
Right.
You're not going to really want to make sure that we can use that definition
No.
like in our sleep. We're going to be okay if we memorize it.
Yeah, I'm okay. If just memorize these. I'm not going to ask you to prove any of those on the exam. But remember, the trig functions are really just based off sine and cosine. The other 4 trig functions are just combinations of sine and cosine. So, if this were, 1,000 years ago, and we were determining how to find derivatives of all of the trig functions, we only need to focus on sine and cosine. Because if once we have the derivative of sine and cosine, if I ask then, what's the derivative of tangent? Then, yeah, of course I could go through the lengthy limit process, h approaches 0, et cetera, or I can say, well, since I have the identity that tangent is sine over cosine, and I have a quotient rule, then I can just find the derivative of tangent by expressing it in terms of sines and cosines, and then using the quotient rule. So I'll say that's the bottom times the derivative of the top. Let me do this over here. I'm running out of room. Okay. So bottom function times the derivative of the top minus the top times the derivative of the bottom, all over the bottom square. So then the derivative of sine is what?
Cosine.
Cosine. Derivative of cosine
Negative sign.
is negative sine. So notice what happens in the top. We have cosine times cosine. That's cosine squared. Minus sine times minus sine is sine squared. All over cosine squared. What's cosine squared plus sine squared? 1. So you have 1 over cosine squared. And we know 1 over cosine, the reciprocal is secant. So we have secant squared. Derivative of tangent is secant squared. If you want to know the derivative of secant, you just write it as 1 over cosine. Again, another quotient rule. But surely know those 6 derivatives rather. All right, so then let's find the derivative of e to the x cosine x. What rule do we need here?
Product.
The product of two functions of x. Product rule. We have the first times the derivative of the second plus the second times the derivative of the first. So really the presentation of the 6 derivatives, trig derivatives, is just a small portion of this. Then it's like the rest of it is like product rules, quotient rules, second derivatives, all that kind of stuff. And if you're not in the habit of writing out derivative for each one of these rules as you say the derivative, I would highly recommend refining that. And whenever a derivative pops up in the quotient rule, the product rule, etc., that you just explicitly write it out. I think it's increasingly important once we move into 3.7 that you're doing that, because otherwise it becomes really, really hard to tell when do you stop taking a derivative. So that's just my recommendation. So we have e to the x derivative of cosine minus sine plus derivative of e to the x is e to the x times cosine x. So we could just clean that up. We could say that's e to the x cosine x minus e to the x sine x. I don't think that's a necessary step, but yeah, it looks nicer. Any questions on that? In later sections, you have to then say, well, here's f of x. Where does f of x, for instance, have a horizontal tangent? So then we have to take the derivative, set it equal to 0, and solve for x. So that kind of stuff is imminent. It's just not prevalent in chapter 3. Okay. All right, then we can look at the derivative of tangent over 1 plus tangent. So what rule do we apply here? The quotient rule, so that's going to look like the bottom times the derivative of the top minus the top times the derivative of the bottom. All over the bottom squared. So remember with the quotient rule that 99.9% of the time you don't expand that bottom squared part. You just leave it as it is. There's really hardly ever a reason to expand that.
Isn't the bottom one Pythagorean?
So yeah, the bottom one, is that a Pythagorean identity? 1 plus tangent squared.
Yeah.
Well, expand this out, right? It's 1 plus tangent squared plus 2 tangent x, right? So is that a Pythagorean identity for 1 plus tangent squared plus 2 tangent? No, the Pythagorean identity is for 1 plus tangent squared, not 1 plus tangent quantity squared. So we're going to just leave the denominator as it is. So this is the one here on the left that's secant squared. This one, who knows? Maybe we could say that's secant squared plus 2 tangent, but that's about it. Okay. We're right here. There's tangent x squared. Okay, so let's compute the derivatives here from our quotient rule. 1 plus tangent times the derivative of tangent, which is what? Secant squared. Derivative of tangent is secant squared. Minus tangent. What's the derivative of 1 plus tangent?
It's just secant squared.
Secant squared, right? Because the derivative of the 1 is 0 plus the derivative of tangent is secant squared. So that's the derivative, the unsimplified version of the derivative. A lot of these derivatives are easy to simplify because primarily you want to think about the greatest common factor. That's typically what's involved in simplifying and or solving equations that involve your derivative. So hopefully it's obvious that both of these terms in the numerator have a secant squared in common. If you take out a secant squared from the top, or factor that out rather, we just have 1 plus tangent x here minus this tangent x on top, and then the bottom is still as is.
And the tangent x is a function of no.
Yeah, exactly, because we have 1 plus tangent x minus tangent x, so the tangent on top goes away. And so this is just secant squared over 1 plus tangent, quantity squared. So that's the simplified version of your derivative. Especially with derivatives that have like mixed functions in them, like e to the x sine x or cosine x. This one here where we had secant squared and tangent, you always want to think about just taking out the greatest common factor. And the majority of the time, that will allow you to simplify things. But I think, again, it's worth noting that this stage right here, at this stage, that's completely fine on the exam. Where if it says don't simplify, this is okay for the exam. If the instructions say do not simplify.
denominator on your final answer?
Where? Down here?
Yeah, that's correct.
Yeah. Because we
Yeah, we
We
never
never
did.
touched
We never did anything with the denominator after we took the derivative. Because the derivative of the quotient is just the denominator squared, right? So that's our denominator squared.
Oh,
1 plus tangent minus tangent. The tangent
is is that bottom, I guess the only reason I asked that is because there was one on the homework where I just canceled out one of the denominators.
Sometimes that happens, yeah.
Okay.
If this were just 1 plus tangent on top, then yeah, it would cancel with one of those on the bottom. Yeah. Any other questions on that? Okay. So then finding second derivatives, we take the first derivative of tangent, secant squared. And if we want to take the second derivative, we have to take the derivative of the first derivative. So remember, secant squared is really the same thing as secant x squared. So we have yet to talk about this kind of thing. Notice that this is a composition of two functions. The inner function is secant and the outer function is a squaring function. So this, to take the derivative of this as it is, this is coming in 3.7 when we talk about the chain rule.
The derivative of that which g of x times the derivative of g of x.
Yeah, right. So before we take the second derivative, we're better off writing secant squared as secant times secant, and then applying the product rule. So we have the first times the derivative of the second plus the second times the derivative of the first.
Zero.
The derivative of the whole thing?
Of like, no, of secant x.
No, the derivative of secant is
Double.
secant tangent, right. So we have secant x times secant tangent plus the secant x here times the derivative again, another secant tangent. Yeah, so you just have two of those. We have a secant squared tangent plus secant squared tangent. So you just have two secant squared tangents. So that's your second derivative. Any questions? I don't know. Did you have a dream about it once?
Probably nightmare.
Do you ever have a dream that happens in real life? Yes. Isn't that weird? It's not, I don't think, isn't deja vu though when you have a familiar experience, like, oh, I've passed this black cat standing on this sign before?
It's a glitch in nature.
That's right.
I forgot what why it was.
Yeah, it's almost like you see the future in your dream. It's creepy. Anyways, it's kind of cool though, right?
I don't dreams.
You don't dreams?
I don't have dreams.
Oh, you do. You just don't know. You just don't remember them.
Everyone says. Looks like the future's bleak, huh?
Which would be the second
All right.
prime of tangent.
All right, got off topic. But one last thing I want to mention in this section, find, so if you had to find f prime, and maybe you came across this in the product rule section, but if the function is, let's say 4x squared times tangent x times secant x,
Can you just simplify that?
well, I mean, yeah, we could try to simplify that.
And you it as your two, like your A and your B, you know, your 4x squared, your times derivative of that, et cetera.
Yeah, more or less. The thing I wanted to point out here, though, is since we've got a product of 3 functions of x, and the product rule really only told us how to address 2 functions at a time, and that's how you want to do it. You just want to take this as 2 functions at a time. This is your first function, and this is your second. You'll have another product rule that does show up, but again, if we're just writing these things out as we say derivative, we'll know when to stop taking the derivative.
Could you take 4x squared as your first?
Yeah, you could take 4x squared as your first and then call secant tangent your second, yeah, for sure. And or you could say 4x squared secant x as your first.
Okay.
So we'll take the first times the derivative of the second. Plus the second times the derivative of the first. Okay, so that's it, right? That's what the product rule says to do. If you've got additional derivatives that show up in that process, then just compute them off to the side. So let's take this derivative here and compute that off to the side. So here's our aside. Okay. Yeah. So this again, we're going to ignore our original problem for the moment and start over with this derivative because yet again another product rule. So we'll just apply the product rule again. We have the first times the derivative of the second plus the second times the derivative of the first. So that's how you want to approach functions that have 3 products, 4 products, 5 products, 6 products, etc. So we have 4x squared times the derivative of tangent, which is secant squared, plus we have derivative of 4x squared gives us 8x times tangent. So then all of this stuff needs to go in place of our original computation up there. So all of this is 4x squared secant squared plus 8x tangent x. And then, of course, the derivative of secant, as we saw last example, is secant tangent. So that's how you would handle those. Does anyone have any questions?
Where is this secant squared?
This one?
The squared, yeah. Because it's, the derivative.
Right.
Oh.
Yeah, so right, yeah, from this one here. So I think even if you've got 3 functions of x multiplying, You're essentially, you have to do two product rules. So even in that sense, it can get hard, if you're not writing things out explicitly, it can get hard to determine when do I stop taking a derivative? Have I taken enough derivatives? Are there more left to take? You know, that gets kind of difficult to juggle if you're not writing out the derivatives coming from the formula explicitly. I don't know, maybe you have more success not doing that, but I would doubt it. Some of these things get pretty involved. All right. Any other questions on 3.5? All right then. Well, we'll take a break and then start 3.7.
That was like most of my military career.
But yes, I need to get the house plane for the that's just like a hello.
That's going to happen at every
All right. So 3.7, the chain rule. The chain rule tells us how to differentiate a composition of two or more functions. So there's two different versions presented here, and we'll talk about both of them. Maybe work one example using both of them just to see which one you prefer. I honestly prefer version 2, but it doesn't matter which one you use. It's the same statement. So it says, suppose y equals f of u is differentiable at g of x. And so u is g of x. So we're talking about f of u as f of g of x with a substitution. So the function's differentiable at the inner function, and the inner function is differentiable at x. So what does it mean to be differentiable again? That what?
You have to be continuous. But being continuous doesn't mean you're differentiable.
Right. Remember, differentiability implies continuity. Continuity doesn't imply differentiability. So if I give you a function and say this function's differentiable at 5, what does that mean?
It's continuous at 5.
It means it's continuous at 5, but more specifically, differentiable means that you can compute the derivative at that location. So if it says it's differentiable at the inner function, that just means that that function has a derivative that's defined for all of those x values. The composite function f of g of x is differentiable at x, and its derivative can be expressed in the two ways shown. So here, we'll note what both of these versions are saying here. So version 1 involves a substitution. So when you see this composition, the substitution is to let u equal to g of x, the inner or inside function. So if we allow u to be g of x, the inner function, then you're dealing with f of u, a function of u. So I'll say,
I was gonna say, they really didn't think that through, did they?
yeah. We have f of u, and we also have u equals g of x. So u is g of x, u is a function of x, and f of u, y, is a function of u. So we'll just label it that way. And so the version 1 then says to take the derivative, you've got two things to look at. You have this function that was the result of your substitution, and you have this function. you have two functions, one of x and the other function of u. So it says to take the derivative, then the derivative of the composition f of g of x is thought of as the derivative of of f of u, where u is equal to g of x. So you really have two derivatives to compute. You have to compute the derivative of y with respect, sorry, let me do this in color. You have to compute the derivative of y with respect to u from this function here, because y is a function of u. And then you have to multiply that by the derivative of u with respect to x, because u is a function of x. So that's exactly what you see in version 1, dy over du times du over dx. And then you have to resubstitute. Finally, resub g of x for anywhere you see u. So notice if just from algebraic point of view, if we multiply dy over du times du over dx, what do we get? You just get dy over dx, which is the derivative of y, your composition, with respect to x. So now that's a lot of notation. We'll look at a practical example here in a minute. So that's version 1. Resubstitute, take two separate derivatives, multiply the two derivatives together, and then you resubstitute back for what you allowed u to equal. Version 2, we'll just write it out in words. What version 2 says is it says to take the derivative of a composition, you take the derivative of the outside function and this is important. When we take the derivative of the outside function, leave the inside alone. So we're going to leave the inner function as is. When we take the derivative of the outside function, leave the inner function as it is, and then you multiply that by multiplied by the derivative of the inner function. That's how we can kind of read that in words, or interpret that in words, rather.
What is the,
So-
are we just giving a value? Like, I know it's in the,
So that's where the knowledge of like how functions are put together is important. Because if you're going to say, well, this is my inside function, that's my substitution. So our substitution is the function on the inside, and it really depends on what the function looks like, right? Because it can take, yeah, your inner function is your substitution if you're using version 1. So maybe if we write a few examples of how this is beneficial. Or how this shows up. For example, take the derivative of 2x minus 4 to the 10th power, for instance. It would be highly inefficient to multiply that thing by itself 10 times, to expand it, and then take the derivative of each term. So if you see a function like this, then the inner function here, that's your u. We're going to say, all right, well, if I'm using version 1, I'm going to let u equal 2x minus 4. You know, other variations, I mean, they're pretty much endless, but so take the derivative of e to the power of sine x, or take the derivative of tangent of e to the x squared. So all of those involve a chain rule. Like I said, we'll look at a specific example using both versions. That way you can kind of get a feel for both of them and determine which one you want to use. Okay. Initially, does anyone have any question on either of those? Again, both deal with taking the derivative of a composition or a composite function. So find the derivative of 3x plus 5 to the 100. So let's use version 1, and then we'll look at version 2. Version 1's a little bit more cumbersome, but I think it does have its advantages. I think it can using version 1 can allow you to split up the function to see exactly what's going on. So it does have its advantages, but I think, practically speaking, that you use version 1 a handful of times to get a feel for how things are put together and how it works, and then move on to version 2, because I think it is a little bit less cumbersome. But version 1 says we first have to identify the inside function and then make a substitution for that inside function. So we're going to say version 1 tells us to let u equal to the inner function 3x plus 5. And if you get to looking at various functions and have a hard time determining which one should be the inside and which one's the inside function and which one's the outside function, just think about the in an operational sense. Like if in this function here, if I plugged in an x value, what do I compute first? That's your inner function. What you compute second is considered your outside function. So for e to the sine x, the inner function is the function sine x, because if I plug something in for x, I have to compute the sine of that first before I raise e to that power. If, something like tangent of e to the x squared actually involves 2 chain rules, but again, if you take it piece by piece, I would first have to evaluate x squared and then raise e to that power. So in that sense, I would say my inner function is e to the x squared, and then I would apply tangent to whatever the value of e to the x squared would be. All right, so we're going to let u equal 3x plus 5. And then notice what happens if we let u equal to 3x plus 5, then y becomes u to the 100th power. Does everybody agree with that? So there's our 2 functions. We have to take the derivative of our u substitution, and we have to take the derivative of y in terms of that substitution. So the version 1 says take the derivative of both of these and multiply those together. So I'm just going to back up so I can see what colors I used here. So y was red and g was... Okay. So to calculate the derivative of u with respect... Sorry, that was the other color. To calculate the derivative of u with respect to x, you can... I don't know what's going on there. You can view that as we're just taking the derivative of the function u with respect to x. So that's another way to note that is u prime. So the derivative of u with respect to x is what? 3, right. The derivative of 3x is 3, plus the derivative of 5, which is 0. So the derivative of our substitution with respect to x is 3. The derivative of y with respect to the variable u is what?
100u to the 99.
Yeah, power rule there, 100 times u to the 99. But this derivative is in terms of u. What that actually represents for us is 100 times u, which was 3x plus 5 to the 99. So there's both of our derivatives. To take the derivative of the composition, we just have to multiply these two derivatives together. The derivative of y with respect to x is equal to 3 times 100 3x plus 5 to the 99. Right, yeah, so this, we'll just multiply those two things together, whatever. So we just have 300 times our quantity to the 99th power. Ta-da! Nice. Yeah.
Running out of
I
air.
think
I think you're running out of ink in your pen.
Yeah,
five.
it's totally out of ink. Just shake it up.
So catch it recording.
Yes. Everyone that watches the video will see this.
That's hilarious.
What? Yeah, right.
Insert once
So that is the derivative of 3x plus 5 to the 100
On
power.
that one, how did you? So how did you jump from the derivative of y in relation to x equals 300 times 100?
Oh.
I see what we did, I guess, more so I'm just determining, without the numbers being there, even maybe without that 3 being there,
Uh-huh.
what is just the expression or the equation that you're using?
The more general one?
Yeah.
Or
like
specific to this problem?
I guess probably general.
So the derivative of the original function with respect to x as it was given, that's the same thing as taking the derivative of u with respect to x, and then multiplying that by the derivative of y with respect to u. So that's this one here, that's this one here. So remember that notation,
Okay.
yeah,
I got you now.
the notation here, the du over dx, just means take the derivative of the function we're calling u with respect to the variable x. And then the next one, take the derivative of the function we're calling y with the respect to the variable
Just
u.
u prime times y prime.
Yeah,
That's all it is.
Yep. Yeah, you can view that as u prime, y prime, but we don't write that because when we talk about y prime, we talk about the derivative of that function.
Okay, so it'll almost be like a
Right.
secondary prime.
Yeah.
A sake with it, like a u prime times a y secondary prime.
Right. Like you could call that y1 prime or something like that.
Okay.
Yeah.
Okay.
Any other questions on that? Yeah.
Well, I was gonna ask, so you don't need to simplify it any further by factoring the 300 into everything else?
Oh, yeah, no, that would be really tedious. And that's part of the benefit of the chain rule is it takes a lot of the tediousness out.
Cool.
So version 2, version 2 says to take the derivative of a composition that we look at, well, let's write y prime. To take the derivative of the composition, we take the derivative of the outside function and leave the inside alone. So the derivative of the outside function is just this to the 100th power. So we're going to apply the power rule to that. So there's the derivative of the outside, but we have to leave the inside alone. And then we multiply that by the derivative of the inner function. Does that make sense? That's, again, it's crucial to be able to identify the outer and inner. And of course, the derivative of 3x plus 5 is 3 times the 100. We get the same result. With less steps, but maybe losing a little bit of information about how the process works. So again, the derivative of the outside where the inside is left alone, then you multiply all of that by the derivative of the inside. Any questions? Yeah?
On the example, we have to do both versions.
No, whichever one you want to use. Yeah, so version 1 or 2, I would just recommend that if you're going to use one, that you just stick with it. If you're comfortable transitioning between the two, I think that's great. But yeah, on the exam, either or is fine. Let me see. I'm going to do this. All right, we'll look at a couple more, I guess, with version 1 or version 2. Maybe after this you can kind of get a sense of which one seems more beneficial to you. Okay, so version 1, what is our inner function? X squared plus 1. So our substitution, we're going to let u equal to x squared plus 1. And then, again, that by implication means that y is what in terms of u? Yeah, u to the 1/2 or the square root of u. Okay. So we got to take the derivative of both of these things and then multiply, resubstitute. What's the derivative of u with respect to x? It's 2x. The derivative of y with respect to u? Okay, right, power rule again.
1 over 2 times square root of u.
1 over 2 root u, yeah. We can write it that way as well. All right, so with that one, with your substituted function, y in terms of u, you just want to remember to resubstitute, because we're after the derivative in terms of x, not the derivative in terms of x and u. Okay, so we resubstitute for, after we take the derivative. So substitute, take the derivative of each one, and then resubstitute. Those are the steps. Don't substitute and then take the derivative with the x's involved. All right, and then we just have to take the product of these two things. So y prime is the derivative here, 2x, times the other derivative, 1/2 x squared plus 1 to the negative 1/2. Right. So we'll cancel those two out, those 2's out, and then we just have x times the quantity x squared plus 1 to the negative 1/2. Or if you like, x over the square root of x squared plus 1. So either one's totally fine for the derivative.
The half gives a good read if you multiply cube and half, right?
Correct. Any other questions on that? Version 1? Okay, version 2, I'll rewrite the function here. So if we're not making any substitutions, and just like we did prior to this, if you have to take the derivative of functions that involve radicals, we write those as powers. So our original function is this here. And then the version 2 says we take the derivative of the outer function. What's the outer function? Right. The last operation you perform is taking the square root of all of that stuff, or raising all of that stuff to the 1/2 power. So we take the derivative of that using the power rule. There's the derivative of the outside, leaving the inside alone. And then we multiply by the derivative of the inside. And we see that's the same result. Anyone have any questions? So then, again, you can imagine a function that has a quotient, a product, and a chain rule all in the same function. All right. Can I advance? Does everybody have what they need? So, take the derivative of e to the sine x, using whichever version you want to use. And then we'll work it out using both versions. And I think that'll be the last one we use, both to do so. So give that a shot.
Taking the derivative of the outside would be sine x.
Your outside function is
And
e to
then
the x.
we leave the
Then e to
inside
x, but
alone.
we're doing e to the x, we're just e to the x.
So should be e to the sine x, and then our derivative of that, which would be no, would it be negative or cosine?
No, it's just, that's just cosine.
So it would be e to the cosine x. And then we're multiplying that by the derivative of the inner function, which would just be e to the x.
You've got your function your outer function is e to the x.
Why is your, okay, I mean, that's fine too. That makes
Because you
more
can't-
sense.
You can't do e to the power of sine x, you can't solve that equation without first solving sine x. So the one you have to solve first is your inner equation.
Which would just be e to the x.
Yeah, so your outer function is e to the x, your inner function is
Yeah, but if you're finding the derivative of the outer function, it's just e to the x.
Yes.
That's it. Which means that that would still leave that as sine dx times cosine x.
What I ended up
I don't know if that's the reason of it, but that's the only part that makes sense.
let's look at my derivatives first and then say, okay, based on this, what we do with everything, with the chain rule based on the substitution. So essentially, this is just.
I can't say it.
What you did here is.
No, we were given that. I think
We did one of the proofs,
we did,
but we weren't given the
derivative
derivative.
of that, but we were never, we were just given.
It's like, I'm making a flashcard.
Yeah, that's what I'm saying.
Flashcards, and I have incredibly obscene logic devices
That's good.
that I cannot. You said we can't like be
That's the point.
There's this kid in our chemistry class who says the most obscene things during class, and no one has said anything, but I'm like, bruh.
That's the derivative of function. In theory, they all be upper class, but then you're
There are children doing it. It's me, I'm the children.
So there's one couple of classes, one where I was I just have substitution frequently, but that's only something you actually like I feel comfortable with because I outweigh it. I just have no problems with being face to face with somebody.
Yeah.
What class was it?
So the first one was math, 0.5. They were just being
That's fair.
I will have. So this is shows that people are paying like $500 to $700.
Yeah.
And you're not being.
So would I say why?
Yeah.
Yeah, exactly.
That's kind of how I'm feeling. I'm kind of to the point now where I'm like, Charles, how dare you separate me and Amber? Because I'm paying $600 to take this class. And I would like to pick who I'm sitting next to. We're not disruptive. We're not dicks. He just wants us to experience working with other people. And I have my personal thoughts on this. Yeah, my group sucks that he switched me to, because I'm the smartest one in the group, which is a problem when I got a 64 on the first test. 61.
I gotta explain this
I got a 64. So that's a problem. But the way that I it took me 3 semesters to develop a relationship with Amber, and now he's just forcing me into a social group with people I don't know. I'm like, well, I actually don't want to be here anymore, but that's fine. That's what I'm saying. But I also like Charles. I don't want to disrespect his wishes.
That's your problem.
So you're taking, you have to say you equal the sign. So just put, like, show that you're taking give you.
The number one thing I need help on is that we were deciding which salts were acidic, basic, or neutral, and why that's the case.
I wrote that down and then I stopped.
What's the justification?
My logic is an derivative of the
That's my thing.
Yes.
All right.
Yeah.
Okay.
Yeah, because it's.
Okay.
Yeah, that's what I have.
And then
I'll just explain it all in this will be U prime and it stays the same, that's right. The X just So we already yeah. You can see dy over du, right? Yes, the derivative is this guy, and then we combine these two together. She's like, I never do it.
I'm just gonna go take my tea off and put it
Final
in.
answer? I understand that.
This is why
Extra study so that I can be here.
I know, right?
You chose this path.
It's unpretty.
All right, let's bring it back. It depends on what version you're using, but if you're using version 1, your u is sine x. And again, the original substitution u is based upon the inside function. Which one of those would you compute first? If I plugged in a value of 0, I would have to say it's sine of 0 before I raised e to that power. So sine is the inner function, or the first, and then that makes y a function of u, e to the u, which is e to the sine x. And then we take the derivative of each one individually. Of cosine x is the derivative of sine, and then the derivative of y with respect to u. It's like if y were e to the x, we would say the derivative of y with respect to x is e to the x. This is just the derivative of with respect to u, it's still e to the u, which means that this is actually still e to the sine x. So we just have the product of these two things as the derivative. Or whatever order you like. Now, it's important, we don't get the derivative of exponential functions until later in chapter 3, but is it important to realize to realize when you have a power function versus an exponential function? And exponential functions are always when x is in the power itself, right? So, like this is a power function, this is an exponential function. So you can't take the derivative of this by doing this. Like, that does not work. Exponential functions have their own derivatives. So if you see x or whatever variable you're dealing with in the exponent, never apply the power rule to that because it is an exponential function. Okay. Version 2 for our derivative just says we take the derivative of the outside function and leave the inside function alone. So the derivative of e to a power, assuming the power is not constant, the derivative of e to some function is e to that function times the derivative of that power. I don't know what that is. Looks like a 2. All right, so it's really important to remember this. I'm just going to write it out sort of generally, but if I take the derivative of e to a power, we'll call it f of x, and we'll say that f of x is not a constant. The derivative of e to that power is still e to that power, but we have to multiply also by the derivative of the power. So it doesn't matter how hideous that function of x looks like, or what it is rather, the derivative of e to that power is still e to that power times the derivative of the power. And I mean, even if f of x is constant, it still makes sense, because if I say what's the derivative of, with respect to x of e squared, if we're going off of that, we would say, well, it's e squared times the derivative of the power. So that's just e squared times 0, which is 0, right? And we know that's true. The derivative of a constant is 0. So, maybe I spoke too soon here. The derivative of e to any power is e to that power times the derivative of that power. All of these derivatives that we looked at until this point have been the chain rule. It's just we haven't been writing those out. Like if I look back at what is the derivative of x squared, just for a simple example, let me say it's 2 times x, right? But what we're not seeing is, because it's really not relevant to write it here, is we're also multiplying this by the derivative of the inside function, x, which is, of course, 1, and that's why we don't see the chain rule unfolding when the inside function is just x itself. So we have been doing that all along, we just never wrote it out that way. Because x squared, we would say, well, the inside function is x, the outside function is the squaring function, right? So if you said let u equal to x, then you have the function u squared. That derivative is 2u. Derivative of x is equal to 1, and you multiply these two things together, 2u times 1 is 2u, and since u was x, we get 2x. So however you look at that. But the derivative of e to any power is e to the same power times the derivative of the power. So what's the derivative of e to the 3x?
3.
Right, 3e to the 3x. Derivative is e to the same power times the derivative of the power. What's the derivative of e to the negative x? E to the power? E to the very same power as we started with times the derivative of the power. Derivative of negative x is negative 1. So if k is a real number, what's the derivative of e to the kx? K times e to the kx. There's the function as it is, there's the derivative of the power. Yeah.
Does this only apply when it's e, like if it would say like 4 to the x and you take the derivative of that?
It's
is that
different.
Okay.
It's different, yeah. So this is, it's important to realize that this is for the exponential base e. The other exponentials, base 4, base 7, base 3, those are a little different. What's the derivative of e to the negative 0.01x? Right. Derivative of e to any power is e to the same power. Just write that. Times the derivative of the power, negative 0.01 times x. The derivative of the power is just negative 0.01. Yeah.
That's y prime, right? For the one.
Oh, yeah, thank you. Yep. So how about the derivative of e to the x squared? Somebody that hasn't got a turn, answer.
2x e to the x squared.
Yeah, 2x e to the x squared. It's e to the power times the derivative of the power. E to the 3x cubed minus x squared plus 1. E to the power, original as it is, times the derivative of the power. Fifth. Yeah. We have 9x squared minus 2x times e to the 3x cubed minus x squared plus 1. E to the power, derivative times the derivative of the power. The derivative of e cubed is 0 because it's a constant. But still, again, we get that. Let me scoop that up for you. Like we just wrote that down over on the board, but it's e to that power times the derivative of the power. Does everyone get the motif here? All right, so that's for e raised to some power. You know, there's other combinations of that. For instance, the secant of e to the x. That doesn't apply, right? if we had what's the derivative of this e to the secant of x, then, you know, all those ones we just did apply to that. So you just got to be careful in what you're dealing with. But again, we take the derivative of the outer function and leave the inner function alone. What's the outer function here? Secant.
Secant.
What's the derivative of secant? Secant tangent. So there's that derivative of the outer function. We left the inner function alone. And then we multiply by the derivative of the inner. So we have e to the x times the secant of e to the x times the tangent of e to the x. So that's version 2, of course. Anyone have any questions on that? Okay. Example 5, cosine of e to the sine x. So we take the derivative of the outside and leave the inside alone. The derivative of cosine is what?
Negative sine.
Negative sine. Leaving the inside alone. Oops. So there's the derivative of the outer, leaving the inner alone, multiplied by the derivative of the inner. So that's, the chain rule says to take the derivative, we have to do that. We've got an additional derivative to compute. So then that additional derivative is yet again another chain rule. So if we want to take this off, we already did this, but in practice, you know, we might take this off to the side and then reapply the chain rule to this. So we would say, all right, well, I'm starting over with e to the sine x. I take the derivative of the outer function, leaving the inner function alone, multiply that by the derivative of the inner. So then, as we saw, it's e to the x, sorry, e to the sine x times cosine x. So that has to go in place here for this thing. This is negative sine of e to the sine x multiplied by cosine x times e to the sine x. So other than like rearranging those terms, that's all we can do. Just be mindful that this is the sine of e to the sine x. There's nothing we can do with that to combine with anything else. You've got a sine of something times a cosine times an exponential.
And it's fully simplified like that?
Yeah, it's fully simplified. There's nothing else you could do to that. Does anyone have any questions with what we're doing or how we're doing it? Maybe you have questions, you just don't know what they are at this point. I don't know.
What?
So yeah, I guess, you know, just again, try the homework, and if issues come up, please let me know. I'll be happy to go over those. So cosine of 19 e to the x. So what is the outer function here?
Cosine of u.
Cosine.
That right there, that cosine is the outside function. So we take the derivative of the outside,
Which is negative sine. Right?
yeah, and then we leave the inside alone. And then we multiply by
The derivative sine.
the derivative of the inside. So outside, derivative of the outside, rather, inside left alone. So it's still the sine of all of that, no, sorry, negative sine of all of that. And then we multiply by the derivative of the inner function, cosine 19 e to the x. So like I said, this is where it's beneficial to write out the derivative explicitly because you have another chain rule for this piece right here. If we knew that derivative, we would be done. So off to the side, we're then going to compute the derivative for cosine of 19 e to the x. So with cosine 19 e to the x, what's the outside, or what's the outer function? Cosine, so we're going to take the derivative of the outside. Oops, sorry, went a little too far. Derivative of the outer function, leaving the inside alone. And we multiply that by the derivative of what? 19 e to the x. Derivative of the inside. So what's the derivative of 19 e to the x? So I'm just going to rewrite that term. So be careful. It's not just e to the x, is it? Right, because the 19 is a constant times the function of x. So that 19 is out front times the derivative of e to the x. So we have negative sine of 19 e to the x times 19 e to the x. So with that one, we know we're done taking the derivative because we don't have any more d over dx. So that's the derivative of cosine of 19 e to the x. Does anybody have any questions on that? Derivative of cosine 19 e to the x.
Negative sine pi e to the x.
Oh. Yeah, except for pi doesn't have a circle in it, but
No.
there.
Okay.
All right. So that's the derivative of that. That's sort of a secondary computation though, right? We had the derivative of this function where that just happened to show up as a derivative. So then we have to put that in place of negative sine of cosine 19 e to the x. Oops, I did it again. Times that whole thing that we just had down there, whatever that was. So it's just those two terms multiplied together. Again, this is a single term. It's the sine of that thing right there. It's not, don't get it confused with like it's the sine times that, right? You just got to be really careful with your notation or how you organize this stuff. So we've got a negative 1 times a negative 1. At least we can get rid of that. And otherwise, the order doesn't matter since all of these things are multiplied together. then our sine of 19 e to the x.
Where did the negative sign go?
Yeah, where did the negative go?
There's a -1 here and a -1 here.
Oh, yeah, that makes
Yeah.
sense. Never mind.
Okay, so again, it's worth pointing out, this is one function, this is the other function, and this is the third function. So that's your derivative. Yeah.
Would you ask us to simplify?
No, you can't simplify that
Or, I mean, not the,
from this stage right here.
Yes, from that.
Yeah, that's fine.
Okay.
This is fine if the instructions don't want you to simplify, it's totally fine. Or any combination of those three factors, however you write them. Yeah. Any other questions on that? Yeah.
The only part I'm kind of confused about is when it's the derivative of 19 e to the x, how does that get back to 19 e to the x?
Because the 19 is a constant times that function of x.
Oh, so you just pull it
Yeah,
out? Okay,
right,
got it.
Right, yeah, so this is the derivative of 3 times f of x. Is what this is.
Got it.
All right, so practice those as soon as you can, and let me know if there's any questions, because, you know, with this, the quotient rule, the product rule, the trig functions, you already have a lot to think about. And so the sooner you can do this stuff, the better off you're going to be. Address any issues as they come up. So I'll see y'all Thursday.